Start recording. Yes, you can, if you want to. Okay. Has everybody got the sign-in form? Good. Thumbs up.
I did it till 6:34 for stragglers.
Okay.
Only because I've noticed a few people still I was walking in. I think I saw 2 people.
Okay.
We'll wait for 1.5 minutes.
Did you say 0.5 minutes?
Yes.
Why not 30 seconds? Oh, you said 1.5.
Yes.
I was like, you made that less than so. That's rude. Okay.
Oh.
But what's an election?
You're so
Has
unreal.
maybe 2 notes on his phone.
I can do that.
Oh, well, how are all of you doing?
All of us.
Are you okay? I think I'm okay. Yeah. I'm Alexi. I knew that joke was coming. I hate this guy. Are you guys all done with midterms, or is midterm 2 coming up?
No. Yeah. 2 on mine.
Oh, okay. You have midterm 2?
Yeah, because I'm still in math class, so.
33?
Yeah. Wrong.
Me with 1 C. But it's on optics. I don't think it'll be too bad. You say that.
I didn't
Yeah,
have
but it's
that.
geometry, bro. I suck at geometry.
What do you mean?
Wait until longer. I was more with optics. Oh, EM minus and stuff? Okay. Alright. I think we're gonna start lecture now. So, whether or not you guys are ready, you're stuck. Oh, okay. Alexi, can you do us the honor? Yeah.
Okay, welcome back to lecture 3. First things first, next things next. Okay, no reminders today, but we do have a lot of events coming up next. Okay, so first we'd like to announce that we have our Idea Hacks hackathon coming up. If any of you guys are interested, here's some of the basic information. It's a 36-hour Harvard-based hackathon. We call it the largest Harvard-based hackathon on the West Coast, so very important. It's going to be on Friday, June 20th to Sunday, January 20th to January 22nd. And this year's theme is game time. Everything is free, and to apply and find more info about it, just go to that link right there. It'll also be on the slides, of course, so just check it out later.
In regards to Idea Hacks 2, I was, did you participate in last year? Okay. Me and Theo, I don't know if you know Theo, but they're our secretary this year. We run a team for Idea Hacks. It was super fun. So it was just a good time. You get a day, but you just vibe with friends, get free food, and also integrate your ideas of fruition. So definitely check it out. It's super fun, especially don't be afraid if you're a first year, if you are a first year. Okay, and then in regards to GBs, we actually had our first GB meeting the other night. Well, not meeting, it was pitching our GBs. In terms of why you should join this professional mentorship, there's also mentorship on academics, becoming an IEEE officer if that interests you. There's also career and internship opportunity. Well, talking to us about internship and careers, that includes, we actually have a good lineup. One of the GBs is led by Julie and Bradley. They both have, and Jessica. And together, I think they have a cumulative 8 internships already. So that's really good, especially Bradley. Bradley's intern for Apple, and then Julie's intern for Intel. But everyone else also has great, valuable experience. Just kind of depends on what you want to choose. Also, we have fun socials. We're gonna pitch that, and then find your family with us. It's gonna be cool. So if you guys love IEEE, or you just want to learn more about what you want to do, or what professors would dog off helpful, like definitely check us out. All right, and then for more information, if you guys are interested at all, this is on the slides, so you'll get this. Obviously, when you pitch the slides later, but if you just want to scan the QR code right now, that's also good. And then there's an application. I don't know what the application entails, but I think I have to read through that eventually. But yeah. Okay. Also, me and Craig, we're leading the best GE, so like apply to us because we're academic. We'll help you become academic weapons. So definitely check us out. We're boards in Gen, and it's led by yours truly. You guys love me, right? So yeah.
Okay. Final announcement. I mean, of course, today you all came here, I hope, for a lecture, but also for cake. We're going to have cake at the end of our lecture today because it's my birthday. Thank you to everybody who sang to me at the beginning. So, yeah. Okay, I think next.
Oh, no.
Oh, okay, yay. All right, so now we can actually get into the lecture.
Okay, sweet. So lecture 3, we're going to start off by talking about capacitors, ICs, and 555 timers. I'm going to talk to you about voltage dividers and capacitors, and Miriam's going to help you out for the timer IC. All right, so I kind of just skip this. All right, so for those of you that attended workshops 1, we kind of touched over voltage dividers. So basically, what a voltage divider is two resistors in series. And can someone tell me what two resistors in series have in common? Correct. Okay. But what do they hate about each other? Anyone have an idea, like what two resistors in series might dislike about each other, or like have different? Someone said it. What? Okay.
The voltage drop.
Voltage, correct. Okay. So the way a voltage divider works is you have two resistors in series, and then we trace the voltage across one of them. It's up to you to choose. Obviously, they have the same current through each, but we track that voltage drop. That's good for a lot of applications. What we're going to use it for in ops is going to be with the potentiometer. The potentiometer is basically a version of the voltage divider. Just when you turn it, you have changed the resistance. I don't know about the internal controls, but basically it's like a little I believe it's a copper circle, it's a copper semicircle, and you trace a lot there. That creates a variable resistance, which changes our, the voltage drop across, which is our output voltage. That's what we trace with potentiometer. So it has 3 pins. You have your VCC, which is your power in, your ground, and then whatever voltage we're like measuring. All right. So you guys are already at lecture 3, and it's not really the little kids, boys, everyone game anymore. So right now, we're actually going to have an example. So I need someone to come up here and solve example 1 with what you know. Can any volunteers? Or do you want, actually, I'm going to take a poll. Do you guys want me to go through example 1 first, and then I choose one of you right in for example 2? Raise your hand if you want that. Don't be afraid. Raise your hand. Yeah. If you don't understand, raise your hand. Okay. Sweet. Okay. All right. What's the show? All right. What's this? Yeah.
Okay.
All right. So we have a 5-volt voltage source, right? And then we have 10 ohms here connected with 5 ohms here. And then we are tracing the voltage that's going to go to this load. So we call this a load resistor. That's just common notation. And then in terms of tracking our voltage drop, what do we know about these 2 resistors? What will they share? Will it be current voltage? Correct, right? So that means that the voltage drop across this resistor will be the same across this one, correct? Yes. All right. So using the rules of current, can someone tell me? Well, actually, let's start off with. Can someone tell us the equivalent resistance of the circuit? Can any of you do that for me? Total. Like so with the 10 and the 5. 10, 2.5. Wait. 12.5. So 1.5.
Yeah.
Okay, 1.5 amps. Correct. So that's on that. All right. So what does that mean about the current being supplied by the battery? We kind of just said it, but can someone like revalue? Yes. No. Maybe so. No. You look. Okay. All right. So sweet. We have our current going through here. It's gonna be 1.5 amps, right? So that means that the current across here is gonna be 1.5, right? And then wow, dude, I know this probably a while. Okay. And then this is gonna be actually the current going into this is gonna be 1.5. I feel like I'm missing something. Give me a second.
No, it's 0.4 amps.
0.4.
Yeah, 0.4 amps.
12.5.
Yeah. 5 divided by 12.5.
Yeah.
That's 0.4. Okay. 0.4. 0.4. Okay, and then since they have the same resistance, this is just a nice rule you guys can use. Since they have the same resistance, it's gonna split evenly across. Just like KCL. It's gonna be 0.2. That's just all the facts about the circuit. They're all gonna merge right back at this node. We're gonna give you 0.4. So then we do the current across, so 5 times 0.4. 2. Good job. So 2 volts is going to drop across this. So what does that mean about the remaining 5 volts? I mean, well, 5 minus 2, right? So what voltage is left?
Why 2 volts? 4 volts. 10 ohm. 1.4 amp. 10 ohm.
Oh, who said 2? Oh, okay. My bad. Yeah, good job. So 4 volts. Okay, so we have 4 volts here, right? Okay, so that means how much voltage is going to go across these 2 resistors? 1, right? Okay. So generally, that's just filling out every aspect of the circuit, but there's a simpler way to do it as well. And it's just without using a load resistor, okay? Now, can anyone come up here and kind of like apply a concept which we put on this board to this circuit? Any takers will help you learn. Do you want to go?
I mean, I can do it, but like, I'm not sure if you want me to.
I mean, does anyone else want to try? No? No? Okay, I'll let you try. Is it okay?
Okay, so what's the circuit? And drop. Okay. At 5 volts.
10 ohms.
10 and 5, right?
Yeah.
And we have the voltmeter connected up here. Okay, and so the voltage across that, so the total resistance is 10 in series, so it must be 10 plus 5, which is 15 ohms. And so the current through this circuit, through the battery, has to be 5 divided by 15, which is 1/3 of an amp. And since it's in series, it has to be 1/3 of an amp through the whole thing. And so the voltage across this resistor must be V equals IR, which is 1/3 times 5, which is 5/3, which is 1.66.
Sweet. Good job. Does everyone understand how we got that for the 2 different types of circuits, right? Okay. So can you move to the next slide? Oh wait, did you pick 2? I'm pretty sure we had another. No?
No,
Oh. Okay. All right. So there's actually a nice little equation which we like to use for voltage dividers, and that's going to be whatever. So let's say we have an arbitrary power source, right, like a battery. Okay. Then we have the two resistors. I really like the chalkboard, so I'm sorry for people who are online watching this lecture if they can even hear me. I really like the chalkboard.
It's probably just quiet.
Okay. And then, so we have an arbitrary battery, right? And we have like two resistors, R1 and R2, right? So the way that we can write a voltage divider expression, right, is that the voltage, we'll call this V2, call this V1, right? Okay, so a version of an equation which we can do this quick and solve it very fast is going to be whatever resistor that we want to use. So this is going to be R2. Let's say we want to find the voltage across R2, right? So we R2 over the sum of the resistances times, well, the voltage of the source. So in this case, it's going to be the EMF. And this is an equation which you can then apply also to here. For R1, it's going to be R1 on top, R1 plus R2, E. Okay? That's a good way to get a feel for what you're going to calculate in the future. This will get you V2. This will get you V1. All right. Does that make sense? So everyone, do you want me to like go through like kind of how we got here and then interest in that? No. Okay. All right. Lexi. All right. Now for the next part. So what is a capacitor? So a capacitor stores electrical energy, right? And it has a capacitance of how much charge it is. It's in farads. You'll never encounter something that's actually a full farad. It's I don't know why they didn't make it smaller, but in terms of what you'll usually deal with, it's micro or milli. 90% of the time you deal with micro or nano actually, but I've seen 1 milli before, and that was in a physics lecture. But it was massive. The capacitor was like this big, huge box, right? And then in terms of what capacitors we use parallel plate capacitors. And the way this works is you have two parallel plates, typically with something we call a dielectric in the inside. You don't really need to know what that does. It just helps with electron flow. And the way our capacitors look is we wrap it in a tight wound circle. So every capacitor you'll deal with in ops in particular kind of has this like cylindrical shape, and that's because parallel plates are being wrapped into a tight cylinder. And that's just to save space, because obviously if we had like something super long like the parallel plates in general, it's not going to have too much space if you have in your circuit and you have like this like chunk. It's not very good for you guys. So that's why we move them into cylinders. Sweet. So if any of you don't know how capacitors work already, they work through charging and discharging. A capacitor charges by having electrons flow through the circuit, and they build up on one side. And then eventually, current doesn't flow because the capacitor gets maxed out. So in the case of this example, I'm going to erase this. You guys good if I erase this? Yeah? All right. Okay. In terms of, let's say we just have a charging capacitor. Something like this, a very simple circuit. The way this works is you're gonna have charge build up on one end, and then eventually current won't flow because the capacitor will be equal to, well, in this case, it'll be like somewhat equal to the EMF of the battery, and then the capacitor won't like have any more change. And then after that, let's say we had a switch here, and I'm gonna add a resistor here, so actually it's not infinite current. So then if we open the circuit, the capacitor will go through a process called discharging. Sweet. All right, so once it's disconnected from the battery source, or voltage source, the charge will flow freely again, so it won't be built up anymore. Think of it like a dam. So like you have water that rushes to a dam, can't move anywhere, right? But now the dam breaks because civil engineers messed up. And then now you have current flowing back through. This artificial current is created. It's just basically a new form of current. And the capacitor doesn't like being polarized, it likes symmetry. So it'll move until all the charges are back to equilibrium on both plates. And that's when we call the capacitor being discharged. All right. So some general rules about capacitors. You guys learned the rules about resistors on lecture 2, right? Of parallel versus series and how we add them together. With capacitors, it's like the opposite of that. So,
like a spring.
yeah, exactly like a spring. In terms of parallel, we add them up as if they are in series for resistors. I used kind of the same equations so you guys could see the similarities between the two. And then for series, you add them like a resistor in parallel. Okay, and then we won't actually dive into the deep parts about the capacitor equations. These are just good to know. And for like something that I've been approached with, and well, just something that you should know for proportionality reasons, is that your capacitance is going to be proportional to the area of the surface divided by the distance in between the plates. Okay, so what that basically means is that the greater the distance between the plates, right, you're going to have less capacitance because it's going to approach to 0, right? And then if you have less distance in between the plates, what's that going to do to the capacitance? Someone, or cumulative answer. Go up, right? Okay. Then for, let's say we make the surface area smaller. What's going to happen to the capacitance? Right. Okay. So then what if we make the surface area bigger? What's going to happen to the capacitance? All right. So can someone tell me what the best form of capacitor would be based off of this proportional relationship?
Love the surface area lowest distance.
Correct. So that's actually just something good to know for you guys in the future. In terms of what we'll actually use for capacitance here, you'll be given capacitors of exact capacitance. Obviously, we'll test it with multimeter, so you make sure that's near it. It's never exact, unfortunately. Nothing in this world is perfect. But the equation for a capacitor is going to be the current of the capacitor is equal to C, which is the capacitance, times the derivative of the voltage of the capacitor at time. And the graph of the charging capacitor, well actually the graph of the charging capacitor looks something similar to this, and then when it discharges it looks something similar to that. That's just I'm not going to go through the differential equation, but you guys can kind of like picture it kind of in your head, right? There's like an E that gets thrown out there. A 1, it's 1 minus E. Yeah, okay. And then for what we deal with RC circuits, which is a form of where you have a voltage source, then you have a resistor, and you also have a capacitor. It can also be in the form of parallel. I'm realizing I overlap, apologize. And we call the time constant of these circuits tau, and tau is just the resistance on the capacitance. You'll learn that if you actually multiply the units of these two, it does come out to seconds, so it's a time constant here. It's actually really interesting how those come to be. A lot of things just cancel out, and it's nice. I mean, it's not nice in the beginning, but it gets nice in the beginning. And then something also good to know is that we like to call it around 4 or 5 time constants, the capacitor will be fully discharged, right?
Fully charged or fully discharged.
Yeah, exactly. Yeah. Okay, so we'll have a time constant around 4 or 5 time constants. You're gonna have it fully discharged, but or charged. And then in terms of what tau actually means, just by itself, you're looking at around 63% of maximum capacity being reached. So either charged or like discharged. So, yeah. Next. Thanks, Miriam.
Right for now. Okay, so now we're going to start talking about 5x5 timers, which is what you're going to need on your project too. So if you've zoned out until now, start paying attention. We're first going to talk about integrated circuits. I'll get to the 5x5 timer, and then we'll start talking about, well, we won't really talk about pianos, but there is a piano we'll get into. Okay, so first of all, what is an integrated circuit? So up until now, we've kind of mostly dealt with like these little singular components like LEDs, just talked about capacitors and resistors and things like that. The integrated circuits are essentially a giant conglomeration of all those things smashed into a teeny tiny little package that you can use with each other. As you can see, that's like a PCB board right there. If you like rip open your computer, you might see something like that. And all those little black boxes are integrated circuits. So there are a couple of circuits printed on a high semiconductor chip, and it removes the need for making extensive and expensive circuits with individual components. So we can look at our advantages. They're cheap, they are small, and because they are cheap and small, they are very easy to replace and mass produce. And also they allow us to use a black box approach, which I'll talk about more later, but essentially you don't need to know like what's inside of an integrated circuit to use it, which makes it really nice. We'll talk also about the issues on the next slide. So here's some of the issues that you really need to keep in mind when you're using integrated circuits. First of all, they can be kind of fragile because we are going to be handling them. You want to make sure that you're not bending and breaking your leads, otherwise we'll have to throw that in one way because you won't be able to use them with your breadboards. Second, orientation. You have to make sure it's oriented correctly because well, you can kind of see there is a top and a bottom, and each of the pins have different functions. So if you flip it the other way and you wire it as if it was right side up, it's not going to work correctly. So you want to make sure that you look at the top of your integrated circuit and see that little divot in it. That means that's the top of it. And that other little dot also shows where your pin 1 is. So that's very helpful to make sure that you have your thing oriented correctly. Question?
But what about the bottom dot? What does that mean? You see it on the thing? Does that mean anything?
I don't know.
I know. It doesn't.
Okay, the bottom dot doesn't mean anything. Okay, so number 3, it is a black box. So you are only considering input and output and not any of the internal behavior of the integrated circuit. The pros of this, of course, is that we don't need to know what's going on inside of it. The con is that if you just look at an integrated circuit, you will have no idea what it does. So you're going to need to use the data sheet a lot to figure out what your integrated circuit is supposed to do and how you're supposed to use it. So that's kind of like an illustration of what a black box is. You have an input, black box does stuff, you get an output. And those things on the bottom are examples of data sheets. And as an electrical engineer, you will get very familiar with reading data sheets. All right, next slide. So what is the 555 timer? The 555 timer is an integrated circuit that is useful for timing applications, which is why we call it 555 timer. So it has a bunch of different modes that you can put it in depending on what kind of components that you place around it. We'll get more into that a little bit. So because it has many modes, it is very versatile, and it gets its name from 3 5K resistors that are highlighted in blue in that schematic. So you can see in that schematic, we don't want to know actually what is happening in there. So we're not going to worry about it. We're just going to treat it as a black box. So next. So here are some of the modes of operation that you can put it in. We're only going to be looking at the astable operation for project 2, but there are a couple others that you could do. You could do a pulse, a flip-flop, or an inverter. Don't ask me about what those are because I don't know. Okay, so now let's talk about the pinout. This is very important, so if you still haven't woken up yet, please wake up. So pin 1 is going to be ground. You connect that to ground, pretty straightforward. Pin 8 is going to be power. You're going to connect that to your 5 volts, also straightforward. So pin 5 is going to be your control voltage. And for our cases, we are going to be connecting it to ground with a small capacitor to remove fluctuations. And pin 4 is going to be reset, and that will reset our timer when it's at low. Next slide. Okay, these are the rest of them. So 3 is our output, and it will output high or low, and the frequency of that is going to be controlled by the circuit. So that's kind of like we saw on the previous slide how it had like the oscillation going up and down. That's basically where the oscillation is coming from. That's the pin that is oscillating, essentially. You're going to have your trigger pin, which turns out to high when the voltage of the capacitor is less than 1/3 of the voltage of the other capacitor. You have the discharge. The discharge is C2. Okay, this is just a lot of like jargon and stuff. If you want to actually know how it works, you can look into all these things here. But this one over here is basically the setup that we're going to be using for project 2. So we have like our C1 or C2, a couple resistors out there, and resistor 3. And we're going to talk about what those resistors are actually going to be doing. Click on the next slide. Great, so we're going to be using as I mentioned, we're going to be using our 555 timer as an oscillator. So our blink timing is going to be dictated by these formulas, essentially. So we have our time on is going to be 0.69 times the capacitor 2 times R1 plus R2, and our time off is going to be 0.69 times capacitor 2 times R1. We're going to be figuring all that out when we set up our circuit in Project 2. Something to keep in mind, like how I mentioned the piano, we are going to have sound frequencies that you're going to need to tune. So just remember that low resistance means a shorter on and off time. You can kind of see that in our timer or timing equations. And then a higher frequency is going to mean a higher pitch. Okay, next slide. All right, so this is Project 2. You're going to be making a LED blink, and you're also going to be making a piano in Part 2 using our oscillator. Okay. And that is essentially our entire lecture today. Thank you, everybody. Hopefully, I think we have cake serving soon.
Oh. Okay. And then in terms of Project 2, we're gonna release the spec soon after this. If not soon after this, tomorrow morning, you'll definitely see it. It just depends if I literally go home and crash. It's been very tired, as many of you probably have felt.
I will definitely post the spec on the master sheet if you guys all have that link. And then also keep in mind that we're going to be having a work session next Wednesday, so just like a week from today, 6 p.m. in the IEEE lab as usual. So you can please attend then to ask for help because, you know, 555 timer is a little bit confusing if you don't know much about integrated circuits. So just let us know if you have questions, get started on it early, because there are 2 parts.
Oh, and then you'll notice also, usually we were going to have the project due dates every Sunday at 11:59. But Miriam's really nice, so we moved it to Wednesday of that same week. But like, you guys have 3 extra days for it. Just because you have 3 extra days doesn't mean you should start 3 days later. Because if you're anything like me, when I first began doing any projects here in college, starting it late isn't a good idea. If you're like, especially if you're in like CS 32, definitely, if you guys, when you guys take that concept, you're not taking it right now, you definitely should start ASAP, because that'll definitely help you out. Or you can be like Alexi and do it the day before.
Don't listen to him.
Cry. But yeah, if you guys have any questions, feel free to stay with us after we hand out the cake. But for the meantime, come grab a slice. We have plenty. We have chocolate and vanilla. She hasn't seen the chocolate, but it's pretty cool. I almost got hit by a car riding a bird. It's pretty cool. It's LA drivers, guys. So thank you for showing up. And
How'd you carry it? You want a bird?
I rode a bird there.
Okay.
And then I walked back.
I was gonna say.
No, I didn't carry it back. That'd be bad. Okay.
What's that say?
Oh, is this night? Is it
Don't even have a
Wait, so it's still on the 23rd? We're doing on the spreadsheet it says 23rd.
Take a picture with you and your
It's your
my
birthday.
It's your birthday.
My 2 birthday cakes.
Where'd she go? Recording to be stopped shortly. Stop recording.